Hello folks. So today I wanted to do something a little bit simpler than these previous tutorials, but this is an effect that a lot of people have expressed interest in and a lot of people have asked me for sort of a HIP file for. I will make that file available, but I thought I would kind of go through this process because it's actually a relatively simple effect, but it's kind of fun. So we're going to look at a few different examples here. I'm going to walk you through kind of the most straightforward example that covers pretty much most of the bases. We'll build that one from scratch, and then I'll show you a couple of other versions that you can apply more generally, and I'll kind of point out the differences that go into those. So let's get started. So we'll drop down a geometry node. Let's just call this pop tearing, and we'll dive inside. And the first thing that we're going to want is just a grid. What we're going to do is basically tear a single sheet and sort of a flat plane to begin with. So we're just going to use this grid as kind of our template for that. And this is going to be a lot bigger than I want, so I'm just going to scale this down to 1 by 1. So this is about the size that we'll be working with here. And for later purposes, I'm actually going to drop the rows and columns just down to 2 and 2. So we basically just have this single panel here, one primitive. That's exactly what we want. Now we're going to want this to be layered to give ourselves that nice sort of layered tearing effect. And to do that, the easiest way is just to do a copy transform. And here we can set sort of the total number of copies we want to make, and all we'll do is we'll translate them up by some amount here. So both of these sort of factors, how far I want it translated and how many layers, these are the kinds of things that I want to be in a parameter, because I'm going to be using sort of these details over and over and over again, so I want them somewhere convenient. So let's drop down a null here. I'm going to call that parameters. I'm going to give it a shape and a color here, so I just differentiate it. And then I'll just toggle this wheel here, go to edit parameter interface, and we're just going to add a couple of parameters. So first I want a p-scale value, and I'll just call this p-scale. I'm going to want an integer value for the number of layers, so I'll just call that num layers, number of layers. And the last thing I'm going to need is also going to be an integer value, and this will be basically points per layer. So I'll call this points per layer. Layer. There we go. Apply and accept. So we have these three parameters, and this will drive pretty much everything. So I'm just going to put some values in here. I'm going to make the p-scale quite small. I don't really want my grains colliding very much, and I want my layers to be nice and close together. That'll give it that sort of rich kind of tapestry feel to it. I'm going to start with some relatively low values here, just so we can actually sim this in reasonable time. So we'll do about 5 layers, 5,000 points per layer. That should be plenty to sort of get a visualization of it, but also fast enough that we can kind of sim it and work through this live. Okay, so with those values, we can start to set up this. So for the total number, well, that's just our number of layers here. So I'll go ahead and copy that parameter and just paste that right in here, paste relative references. And then for the translate, I want to translate it in Y, so I want to stack them vertically. And I want to translate it basically, I want the distance between the layers to be some proportion of p-scale. And I want it to be a little bit more than 2 times p-scale, just so we don't have any overlaps. So I'm going to grab this, I'm going to copy that parameter. I'm going to just start and paste that in here. And I'll just multiply that by, say, 2.1, so just a little bit more than 2. So that'll space those out. So if we take a look here, sure enough, we've got 5 very closely spaced planes here. Perfect. Now the last thing I want to do on this node is actually go down here to this copy number attribute, because I actually want to sort of keep track of which of these planes is which layer. And I'm going to rename this right away just so it's more transparent to layer. And so now if we look on the primitive level here, we can see that each of these has its own layer number ranging from 0 to 4, so that's perfect. So now that we've got our layers, we want to add some points on here. So to do that, what we're going to do first is just add points on each layer. So we're going to do a for each, and it's going to be for each connected piece. We don't need this connectivity node, we basically have connectivity already. And so we're just going to go to this last node here, and we're going to say our piece attribute is actually layer, and that's on the primitives. So sure enough, it reflects that we have 5 layers here. Now all we really need to do is we're going to scatter some points, and we know how many points we want to scatter. We have that information up here. That's our points per layer. So I'll just copy that And again, paste relative references here. And the other thing we're probably going to want to do is have this different per layer, because right now if we ran this for each layer, if I just do the points here, you'll see they all stack perfectly. They're exactly on top of each other because we have the same seed for each layer. If we go to scatter, this global seed right here. So what we can do instead is we can go up to this and click on this create meta import node. And that basically just creates a little node here that stores a detail attribute each time we go through. And it actually stores several detail attributes. It tells us the iteration, the total number of iterations, the value for the attribute that's being looped over, and the sort of integer value of that attribute if it happens to be a floating point. So we can use pretty much any of these, but iteration is probably the simplest. And basically what we can do is just reference this node and this value here in our seed. So I'm just going to call this loop meta because it's a very long name, so it's easier to just kind of shorten that. If you have lots of different loops, you might want to keep that sort of for each begin one loop meta, but this is really the only time we're going to use a loop in this setup, so we can just shorten that. So we'll go down to our global seed here, and we just want to reference that detail attribute. So we'll say detail, and we want to go to this loop meta node. We want to grab iteration, and we want the first component of that value. It only has a single component, but we still need to specify that. So if we do that, now we can see that our points are no longer sort of stacked. They're no longer overlapping in the same way. They're jittered on each independent plane, and that's pretty much what we want here. Relaxation is probably good at 10. That's going to be no problem. We don't really want it over relaxed. You know, we don't want to go crazy high and have them like really uniformly spread out. I mean, that was really high. I probably shouldn't have done that. But if we just let that finish, it's only 5,000 points. Yeah, so, you know, if you relax it too much, then it starts to become highly regular again, because it's basically just finding this sort of space maximization here. But anyway, the default there is just fine. So we'll go back to 10. So we want to scatter points for each layer, and we also actually want to do our connectivity here. So we're going to drop a connect adjacent pieces, and this is going to start to set up the lines between our different constraints here. We don't actually have pieces, we just want to drop down to adjacent points. So we're actually going to use individual points here. Assuming uniform radius is fine, this search radius is pretty good, this is way too many points. I'm going to drop this down to something like 8. And finally, I do actually want it to produce rest length, because that's something that the pop solver is going to use, so we might as well just have it computed right away. So if we do this and pipe it through, what is it complaining about? Yeah, it's not using an attribute name, so this doesn't matter at all, so don't worry about that warning. So now we've got each individual layer, and there's a bunch of sort of connections on each of those layers. So if I just output sort of one of these, you can see we get kind of a layer like this. So that's a single layer. So we're getting 5 of these layers, and they have sort of these constraints. These are the strands that are going to be breaking when we start to do the tearing. The other thing I want to do, though, is actually add strands between these layers. So to do that, I'm just going to sort of come back out here. I'll just drop a null so we have somewhere to branch off from. And I'm actually just going to do another connect adjacent pieces here. And again, we're connecting points. This radius is fine. And I don't even want that full 8. I'm going to drop this to something like 4. And again, I do want rest length. Now, if we had done, let me just drop another connect adjacent pieces here. If we were doing adjacent pieces from points, if we had sort of piece attributes, and you know, we could do various ways to sort of set this up here, we could use this handy find boundary connections, and we could add as a cluster attribute our layer, and that would only generate connections between adjacent layers. Unfortunately, when you're connecting by points, it doesn't give you that option. You don't get to do that. So when we've done this connection, we actually have a mix of connections within layer and between layer, and all I really want here are the between layer connections. So what I'm going to do is just do a primitive wrangle here. And what we're basically going to check is we're just going to say for each of these sort of constraints, for each of these edges it just produced, we're going to get rid of them if they're between sort of points in the same layer. So I'm going to go ahead and grab those 2 points. So I'm going to say point 0 is prim point from this geometry, this primitive number, point 0, and point 1 is prim point, this geometry, this primitive, and 1. And again, we're dealing with edges. We know that they have 2 points each. We don't really have to worry about anything else. So the layer values, we'll have layer 0 is point 0 layer and at pt. I'm going to have to fix something before this works, but we'll get to that in a second. So let me just put pt 0, and layer 1 is going to be point 0 layer pt1. And basically what we'll say is if the layers are the same, so if layer 0 equals layer 1, then we're going to remove this prim. And we can get rid of its points too. Now, initially this isn't going to work. So if we look at these points here, we don't have a layer attribute here. And the reason is because we never sort of brought it over. But we can actually do that on the scatter node. So there's this tab that you often don't look at, the output attributes. And if you go over here, basically what it says is all the point attributes on the geometry it's being scattered on will be copied. So that's that asterisk here. Nothing else is going to be copied over. So in our input geometry here, we have layer sitting on primitives. So what we can do is on the scatter node, we can say primitive attributes bring over layer. So every point you scatter on this sort of primitive, copy over that layer attribute to that point. So if we come back out here, now you can see we have this layer attribute, and it ranges from 0 to 4. So if we do that now, then we can reduce these primitives. So once we get rid of those, you can see we only have these ones that are between layers now. So here we have our between layer attributes, or sorry, connections, and here we have our within layer. So to get all the different ones that we want, we're just going to merge that together. And so now we have constraints within layer and constraints between layers. So we have this nice sort of setup of all of our points that we're going to feed into the pop solver and all the connections between them. Now, because we've basically taken all of these points here and made a bunch of connections and we have all of them here, you'll see that if we think about how many points we should have, well, we have 5 layers and 5,000 each. We should have 25,000 points. If we look here, we actually have almost 50,000. And the reason is we're basically branching both of these. We're sort of duplicating these points. So we can solve that really easily. We'll just drop down a fuse. And that's just going to sort of lump together the points that are in the same place. And now we're back down to the expected 25,000. So that's all good. The next thing we want to do is we just want to set a few properties that are going to be necessary for the pop solver. So I'm going to drop down an attribute wrangle just to set the p-scale. So I'll call this set p-scale. And we've got that again in our parameters. So I'll just grab this value, copy parameter, oops, paste relative references. This gives us a funny channel string that's sort of backticked, so we can just get rid of that stuff. And we'll just say at p-scale equals that channel. So now we have our p-scale value on these points. The POPnet will want that, otherwise it will assume it's 1 and then it will just explode because that's much too large. So we've got our p-scale. And the last thing we want to do is set up our constraint properties. So constraints are primitives, so we're going to use a primitive wrangle. We'll call this constraint properties. And we don't need too much here. This is a basic POPnet, so these aren't sort of complicated constraints like you would see in a rigid body simulation. But there are still some parameters we're going to want. And in particular, we're going to want to sort of vary the strength of these different constraints. And broadly what I want to do is make the bottom pretty tough and the top relatively weak. So that means once it starts tearing, it'll tear from the top and it'll sort of spread out, and then it'll only gradually tear at the bottom. So we'll get a nice layered effect there. So what we're going to want is to set a strength value. So I'll say at strength, I'll just give it a default just to make sure that whatever else I do, at least everything has a single strength value. And then what I want to do is sort of base this on layer. So right now, if we look at our sort of points here, or at our copies, our layers are starting from the original one at the ground, so the lower one, and they're going up to the maximum one at the top. So if I select this top primitive here, and we just show only selected, and we go over to primitive view, this is layer 4. If I select the bottom one here, you can see that's layer 0. So we're going from 0 to 4, bottom to top. And so we want our strongest constraints to be on the bottom and our weakest ones on the top. So what we can do is get the layer of this current constraint. And so to do that, we're going to have to sort of grab it from the points, because our layer, if we go back to our constraints here, we don't have anything except for rest length on the primitives. Everything is sort of sitting on the individual points. So I'll just grab the layer, and I'm going to grab this, actually, I'm going to cast it as a float. And the reason is I'm going to want to divide it. So I'm just going to sort of say that this is a float, and we're going to grab the point attribute layer, and I don't really care which point I take it from the sort of from the original primitive. So I know some of these constraints are going to be spanning layers, so they might have two different layers for each of the two different points. I'm not really going to worry about that. I'm just going to grab sort of the first point on each primitive. If you want to get fancy, you could do the average here. You could grab each of them and then sort of take their midpoint, but this just seems easier to me. So I'm going to grab the layer from the point, and I want to grab the max layer, and I'm just going to grab that actually from our parameters. Oops, I'm doing this inside the wrong wrangle here. I'm just going to cut those and put that back down here. This is where I want that. So I'm going to grab the layer, and then I need the max layer. So often what will happen when you're copying over parameter values, I find this very frustrating, so I'm going to copy this just to demonstrate. If I go up to my parameters here, and I grab this number of layers, that's the value I want, I copy parameters. If I come down here and go here and say paste relative reference, it deletes everything. It gets rid of everything in here. I've had this happen a number of times and I find it very frustrating. What you can do instead, I find, as just sort of a workaround so you don't have to create a new node and paste it in there. So sometimes what you can do is just add a new attribute wrangle then, and sort of paste it in here. Whoops. Paste relative references here, and then sort of grab this and move it over. So you can do that. Or as long as you're not using groups, you can just paste it into one of these other fields just to have it available. And then you can just grab it from there. So I'll say, okay, here's my max layer. I'm going to call it a float, even though I know it's not. So I'm going to grab it as a float, and I'm going to subtract 1. And the reason our max layer is, or our sort of number of layers is 5, but our maximum layer is 4. So I want this value to be 4. Okay, so I've got our current layer and our maximum layer. Now what I want to basically do is sort of multiply the strength by the layer. But I don't want to multiply actually it directly by the layer, because the layers are going from sort of 0 to 4, but I want them to be going sort of strong to weak in that sense. So I'm going to invert these values. So I'll call this invert layer, and I'm just going to say that that's going to be max layer minus layer. So now our layers range, instead of from 0 to 4, they range from 4 to 0. And so the weakest is going to be 0, and the strongest is going to be 4. And that makes good sense to me. So the last thing I'm going to do, I'm going to create sort of a multiplier. So I'll call this strength for strength multiplier. And what I'm going to do is I'm just going to take a number greater than 1 and raise it to the power of this inverted layer. And so what we're saying is layer 0 is going to be sort of 1.1. Actually, it's going to be 1. Layer 1 is going to be 1.1 to the power of 1. Layer 2 is going to be 1.1 squared. Layer 3 is going to be 1.1 cubed. Layer 4 is going to be 1.1 to the power of 4. So they're going to get stronger and stronger and stronger each time we move up a layer. And so the last thing I'll do is just set our strength. We're going to multiply it by this strength value. So doing this strength up here is completely redundant at this point, but if we start to get more complicated with this setup, I just like to make sure at the very beginning sort of everything is initialized, because otherwise if I forget something, if I have a bunch of conditionals and I miss a particular case, then those strength values will be at 0. So this way at least I know that they have a basic initial value. This also gives me a very ready scaling. So I've got this sort of per layer scaling handled here, but if I wanted everything to be sort of twice as strong, I can just adjust it first. So that's why I've got this value in both places here. So that sets up our constraint properties. Oops, I'm still in select mode here. Get back to my camera. So that sets up our constraint properties. The last thing I want to do here before we kind of move on into the next step is just add something so we can visualize a little bit. And what I'll do is I'll just drop a color on the points. and I'll make this a ramp from attribute, and the attribute will be layer, and I'm going to copy over our number of layers here. So I'm going to copy this into the max. And again, we'll subtract 1. So we're going from 0 to 4 here. And this just gives us sort of, should be giving us some color that varies across layers, but it does not seem to be. And why is that? We have a point attribute. It's called layer. It ranges from 0 to 4. Is this being upset about that parameter? 0 to 4. Oh, here we go. All right, it just needed to be refreshed for some reason. Okay, so that works fine. So now we've got our layers sort of colored here, and this will just let us keep track of what's going on as opposed to having them all white. I find this default spectrum from black to white is actually sort of, it doesn't have very high contrast, so I might even drop another color in the middle here. Let's just drop a nice blue there. Okay, so that gives us some good layering. We'll be able to see what's going on now. Okay, so we've got our basic geometry here. This is what we're going to feed into our pop simulation. But the basic logic of what we want to do here is sort of have something that triggers some of these connections to start to sort of stretch or to put them under strain. And the way that I'm going to do this, so you could do it in a lot of ways. So an alternative to what I'm about to do would be to sort of have a basic infections type thing. So you could set up a single point as a seed point and then have some sort of spreading infection. Control that with noise. You could do all sorts of different things. What I'm going to do is do a collision-based method. So I'm going to have some proxy geometry we're never going to render, and I'm going to have the collision in that geometry with this trigger the sort of tearing events. So we're going to set up that collision. So we'll do that over here. And what I'll do is I'll just start with a sphere. I'm going to turn this into a polygon, give it some nice high resolution. This sphere is awfully big compared to what we're dealing with, so let's scale it down, maybe 0.4. I'll call it 0.5. And then I want to put some noise on here. So we'll put a mountain on there. That's actually looking pretty good to me already. You could sort of play with some of this a little bit, get some more sort of smaller features. Maybe that's looking pretty good. Doesn't need to be nearly so rough. Let's make it nice and smooth. We're not going to be worried about a lot of the details of this. We're just using it as sort of a collision geometry. Okay, so that's actually looking pretty all right to me. Next, I'm going to turn this into a VDB. So VDB from polygons. And the reason is we're going to use a surface distance representation to understand whether or not a point is inside of this geometry. So we're going to do that kind of a test. So we want to make this surface volume. This representation is okay, but we could get a little bit more precise, I think. So let's just drop that down a bit. We'll get it even higher resolution. We only have to calculate this once, so we can afford to sort of be pretty precise about it. That's looking pretty good to me. Okay, so then the last thing I want to do is sort of animate its collision with this geometry. So right now it's just sitting right on top, and it would immediately start sort of having its influence, and I want it to kind of spread a little bit. So what I'll do is I'll just drop a transform here, and we're going to start at frame 1 here, and let's just look at this from the front. And what I'm going to do is just raise this up until it's just about to intersect. So here it's actually already intersecting just a little bit, so I'll pull it up just a tiny bit more, somewhere around there. So I'm going to keyframe that, so you can just alt-click here, so that sets a keyframe at frame 1. And then what we want to do is at some point later, let's say by frame 120, we want it to be pretty much sort of right in the thick of things, so maybe way down here. So you can see that this has gone this funny green color. That's basically saying, okay, this keyframe value has changed. These two are in this blue because they've been keyframed, but you haven't actually changed them. But overall, this is just saying, okay, some values have changed here, so we can just alt-click again, and this sets a new keyframe. So now as we scrub between, it'll just animate between those 2 points, and that's pretty much perfect. So now we've got our basic sort of pop geometry, and we've got our collision geometry here, so that'll sort of come through and trigger the spreading. So now we can just dive straight into our pop network. And in fact, we can just use the default POP network. It's going to have some of the nodes we want already set up. And I'm just going to pipe these things right into these inputs here. So I'm going to use our sort of first and our second context geometry inputs on our POPnet. So let's dive inside. So the basic POP network will have our source already set up, but it won't really give us anything else. And in fact, we need to make some changes to this source. The first thing we want to do, we do want to use our first context geometry, but we don't want to scatter onto surfaces as the default. We actually want to bring in all geometry. So we want both the points and the constraints between them. So you can see that that gets brought in here. So we have all of these edges as well. And these constraints are important, so we have to make sure we bring in all geometry. Now the next thing we want to do is we don't want to be spawning points. We don't want to be spawning geometry into this simulation as it continues. We really just want to bring it in on frame 1. So on the birth tab, we're going to go here, and we're going to, under impulse, just say, if the frame is 1, then we're going to bring this stuff in, and every other frame we're going to do nothing. So we're just going to bring in this geometry on the first frame, and then never again. So once we've got this geometry in here, well, what are we going to do with it? So we only need a couple of nodes in here, and the main thing we're going to use is pop grains. And so this is a good way of simulating points and of simulating kind of constraints between them. This has been more or less superseded by vellum grains, but it's just as easy to set up in POP for this particular setup, so I'm just going to sort of go through it in this old POP format. So we've got pop grains, and what we need to do relative to its defaults is turn on a couple of things. And in particular, we want to turn on the explicit constraints here. So this is basically saying, pay attention to edges between points. It's going to treat those as constraints. So same as in any sort of rigid body simulation, edges between points become constraints between points. So we want to turn on these constraints, so we can do that just by setting a weight to 1. If you read any of the documentation, all of your weights should sum to 1. They never do. Even in the default setup, they're already sort of more than that. So we've got sort of internal collisions being 1, and we've got target pins being 1. Really, you can kind of just turn them on or off. It's not technically correct, but generally just setting your weight to 1 is fine. So we're going to turn on our explicit constraints by setting our weight to 1. And we're going to turn on colliding mutually constrained particles. So we want to make sure that the particles that share an edge can actually collide. We don't want them totally slipping through each other. And then the last thing we want, which is pretty critical, is to be able to break constraints. That's the whole tearing effect that we're going for, is to be able to sort of get these constraints to break, to snap over time. When you turn this on, it'll set up this break threshold, and this is a tunable parameter. Through experimentation, you'll figure out where you want it to be. I like a value around 0.3 for this setup, so I'll just dial that straight in here. So with this setup as it is, not much is going to happen. We don't have any other forces going on at the moment. We haven't set up that collision geometry to really do anything. All of our rest lengths are based on where these points exist already, so if we run this, nothing much should happen. It might wobble a little bit, although in this case it's not even doing that. Basically all of these forces are being sort of satisfied. So each of these constraints is basically set up to say, hey, this point where it already is, that's where I want it to be relative to everything else. So far nothing much is going to happen. What we want to do is use that collision geometry, bring that in, and allow that to sort of start to update things here. So we'll do that on a pre-solve, and what we'll use is a geometry wrangle. And what this does is takes whatever geometry is in this object, in this case it's just points and primitives, so that's perfect, and it just manipulates it, and it does that before this solver step on each step. So we'll pipe that in here. And what we want to do here is basically test, for each primitive, is it inside this collision geometry? And if it is, we want to do something to it. And in particular, what we want to do is decrease the rest length that it wants. And that's going to basically try to draw its points together, and that's going to put strain on the points around it. So we're going to shrink each of these rest lengths as they start to collide with that geometry, and that's going to cause them to pull on each other, to pull on their neighbors, and start to tear this network apart. So the first thing we want to do is figure out, is it inside or not? Is it inside of that colliding geometry? So to do that, we need to access that geometry in here, and we can do that by going over to this input tab, and this basically gives us this input 1, 2, 3, and 4 is what we normally think of on wrangles. That's these little knobs, our inputs 1, 2, 3, and 4. And if you open a wrangle, you can see it's a subnet with these sort of separate inputs that are coming in. And so within DOPS, you don't have those toggles because we're not in that context, but you can go to this Inputs tab and basically specify whatever you want to come in and be treated as those inputs. So input 1 is basically the geometry itself. Input 2, we're going to use SOP. And we're going to point to, where are we here? Oh, I should have dropped a null. That would have been useful. Hang on, we don't even have to do that. We actually want our second context geometry. So when we set up our network here, we piped this right into this second input. That's our second context geometry. So we can just reference that directly here. Okay, so what do we want to do in this wrangle? Well, in the code, we want to be able to sample that surface distance function we made. So we can do that easily. We'll call this distance, and this is just going to be a volume sample. And we're sampling the volume on input 1, so that's that second input. And we want to sample the field called surface. So if you remember, we go back here. When we set up this VDB, this distance VDB is called surface. So we want to reference that surface, and we want to test it at the position of this primitive. So that's going to be the midpoint of the primitive. So this will give us a value. Let's go ahead and store that value as an attribute just in case we want it later. And then what we want to test is this distance less than 0? And that's basically asking, are we inside of that collision geometry or are we not? If we are inside, what we want to do is adjust the rest length. And the way we're going to do this, we already have a rest length value. What we're going to do is we're going to multiply it by some value that's going to be less than 1, so we want to shrink it. And what we're going to do is actually sort of have this based on the layer. So we're going to do a fit, and we're going to go from the current layer, and that doesn't exist on the primitive right now, but we'll take care of that in a second. So we're going to go from the primitive layer, we're going to fit that layer in the range 1 to max layer, and that's going to sort of scale our multiplier from 1 to some value less than 1. So none of this information exists yet. Let's go ahead and grab that. So our layer, we're going to get from the points. So we're going to grab that from I just realized this should be a primitive wrangle. Here we go. So we're going to grab that layer from one of the points on this primitive. So we'll just use, again, prim point 0, so just the first point on that primitive. So we'll grab the layer from there. Now it's complaining that max layer doesn't exist, and sure enough it doesn't. So max layer, we need to grab from our parameters. We'll go back up here, grab that again, and we'll do that same trick where we sort of paste relative references in here, and then we can just copy this value. And of course this is saying it's a string, so we'll just change that over and say it's a float. So now we have our layer and our max layer, and what we're going to say is in the range 1 to max layer, so our sort of second to lowest layer to our highest layer, we're going to sort of we're going to multiply in this range. We're going to scale it to this range. And actually what I would like to do here is not quite this. Actually, I think I want to go from 0 to max layer minus 1. So this is going to say that our lowest layer, our bottom layer, we're not actually going to shrink these values at all. Our top layer, we're going to shrink these values each time they're inside by this amount. So our lowest layer is basically never going to get sort of torn apart. It's never going to shrink very much, but our upper layers are going to shrink by this full amount. Layers in between will shrink by, say, 0.99, 0.995, and so on and so forth. So this may seem like not very much shrinking, but remember this happens on every single step. And critically, actually, if you change the substeps, this will happen on every single substep. So this actually starts to happen pretty fast. So this value is already saying like 2% we're going to reduce it every time, and that compounds. So that gets pretty significant pretty quickly. Okay, so once we've done this, our basic setup is almost complete here. And so if we run this, we'll already start to see things, although we're going to notice there are some problems here. So let's just see what happens. thing. Oh. Yeah, I need to feed something into this wrangle, and we want to feed in myself. We want to feed in the current geometry here. So if we run this now, there you go. So we can definitely see something is happening here. We're getting sort of this spreading, and these white lines I think are showing where the constraints are currently relative to the blue, which is our guide geometry. So we can turn that off. So here's our full geometry. So you can see that it's starting to sort of stretch and rend where that collision geometry is coming through. And we can see that really clearly if we come out here. Let's turn on this and take a look at our geometry sort of in this mode. So you can see that as it comes in, it starts to shrink that geometry where it's colliding. And we start to get this nice tearing that starts at the top and then progresses down. And that's because our top layers are weaker and we're shrinking them by more, and our bottom layers are stronger and we're shrinking them by less. So right away we're getting this effect, but as we continue through, you start to see maybe a problem here. These edge pieces are getting sort of bent, they're getting pulled in, so the whole geometry is getting distorted and pulled towards the middle, because we're basically shrinking all of these constraints, and that's pulling all of this outer part inwards. So the way to get around this, the thing that we want to do is basically have some way of keeping the edges in place while allowing the middle to continue to tear, to stretch and sort of rend like this. And so what we're going to do there is we're going to use another aspect of pop grains, which is this very lowest section here, these target pins. And what these pins do is basically specify, if you've provided an attribute for them, where these points should try to stay, where they should try to stick to. So we're going to set up those attributes. And what we want to do is basically have our points stickier to the extent that they're at the edges here, and a lot looser and freer to move to the extent that they're in the middle. So we need some way of measuring how far are each of these points from the edges. So the first thing we'll do is we'll take our original geometry here, our copied geometry, and you'll remember we set up our grid here to only have these 2 rows and columns. That means there's no interior edges at all. So this is handy because it means we can just right away drop down a carve sop and take our U at 0 and our second U at 1. And what we're basically doing is just carving out all the primitives but keeping the edges. So this just leaves us with the outer edges of each of our grid pieces. So that's perfect. The next thing we want to know is how far is each point from these edges. So let's just give ourselves a little bit of space. I'll keep this color way down here because we're going to get rid of it a little bit later. We're going to do all our coloring at the end. This is just for visualizing. So let's just drop another wrangle here. And first we'll just do an attribute wrangle. And we're going to say our edge distance, and we're just going to use XYZ dist. And so that's just going to say how far away is this point from the nearest point on this geometry. So we're going to pass this geometry, and we're going to test this point. Yes. So that'll give us a distance. You can see that right here. And if we visualize this distance, let's just drop a color node. Let's do a ramp from attribute again, and we'll use edge dist. And if we color this, you can see we have sort of black for 0 near the edges, so it's very close to the edge, and it gets sort of brighter and brighter as we get towards the middle here. And the maximum will actually be whatever sort of half of root 2 is. So at any rate, it's gonna be somewhere around maybe 0.6 or so, and that'll get it to white there. So now we have for every point how far away is it from the edge, and we can use this value to drive our stiffness of these pins, and basically say the ones that are near 0 should be really, really stiff, and the ones that are sort of farther away from 0 should be a lot less stiff. So what we can do here is we'll just go down, and we need to put this information on the individual points. So that's why we put edge distance on the points, is because we want this information on these points. So we'll just call this setup pins, and we need a couple of different attributes for this. The first one we need is going to be a vector, and it's called target P. And this is basically where does this point want to be? What are we calling its target? And we want it to just be where the point is to begin with. So that's going to be its anchoring point. That's what it's going to try to reach for. We're also going to set target weight, and we'll just set that to 1. That's basically saying we're going to use this attribute. We're going to use this value. And the last and most important one is going to be target stiffness. And this is going to say how strongly is it going to stick there. And it turns out you don't need to set this very high at all for this to sort of start to have a large effect. So we're going to use this edge distance here. So we're going to fit edge distance, and we're going to say basically in the range of 0 to 0.1, we're going to do this ramp here. And so that's basically going to say, you know, within roughly this kind of a range here, we're going to move from our maximum stiffness to our minimum. That means this entire interior here is going to be our minimum, and we're only going to have this ramp sort of near the edges here. And we're just going to set this fairly low. We're going to go from 0.1 to 0 actually, so it's almost the inverse. That's arbitrary. It could be a little bit higher, but I found that this seems to work reasonably well. So with these values in place, if we just pipe this in instead, now what we can do is go to our target pins, and we're just going to set stiffness down to 1, because stiffness is a multiplier for what we pass in here. So we could set a global value of stiffness here by sliding this scale, or if we set this to 1, it will multiply what we have as an attribute on our points. So if we just use this, now what we should see is that the edges will stay in place while the middle contracts. And sure enough, even as it contracts more and more and more, those edges now aren't caving in. They're all staying where they belong. All the edges are sort of keeping where we want them. And that's giving us the effect that we're looking for here. So it starts to tear as it goes inwards and inwards and inwards. And that gives us our nice setup here. Okay, so this is actually the gist of our effect. This is pretty much what we're looking for here. We're getting all the behavior we like. Now we just want to sort of clean it up for simulation, or sorry, for rendering. And there's a few things here we're going to want to clean up and adjust. So let's take a look at what we want here. The first thing we're going to want to do, so if we just drop a null here so we can look at this information, this is our sim data. Oops, let's just get a T in there. That's our sim data. If we take a look at the attributes, there's just tons of them. And you know, right now this is a pretty light sim. We've only got 25,000 points. For a proper sort of render, you're probably going to want a lot more layers and a lot more points per layer. So the renders I showed at the beginning had like 20 layers and I think about 50,000 points per layer. So that starts to get a little bit more expensive. So in general, you're probably going to want to cache out this simulation. And if you're going to do that, there's no reason to store all of this sort of information. You don't need this information. It's just going to be taking up space. It's not useful to you. So we're going to clean this up. We're going to drop an attribute delete. And what we want to get rid of is almost everything. So we're going to get rid of just about everything from the points. We're going to keep their position. We're going to keep their layer. And that's pretty much all we want from our points. There shouldn't be anything on the vertices, but we'll get rid of all that anyway. On primitives, we might want to keep our rest length just to sort of know what length it is. That's pretty much the only information we have there. We don't need to keep sort of this stiffness stuff that we set up or the strain. You might want to keep strain if you want to visualize that. That's there, that's an option. But basically I'm just going to keep our original rest length here. And then on details, we don't really need this information either. This is just sort of our ID map. So we'll get rid of that as well. So if we take a look at this, you can see that this thing takes about 17.4 megs down here. You can see, if I open up that, you can see down here, this takes about 17.4 megs. After cleaning, we're down to 10. So that's a substantial improvement. So if you're caching this out, this is going to be sort of a lot better. So once we've done that, there's a little bit of extra cleaning we'll probably want to do. So in general, and I'll just drop this here so you sort of have an idea of what you might do, I would put a file cache here. I would sort of cache out this information. Since I'm not doing sort of a full sim at this point, I won't worry about that, but this is where I would put that. Then when you read from your file cache, you can come out and do a little bit of extra cleanup. And the first thing you might want to do, if I sort of look at this sim here, oops, I don't want that at all. When I look at this, I don't like all these loose points. I don't want these to be here. I don't want to really see all these sort of loose extraneous points here. So what I might do is basically say, well, any point that's not connected to anything, I'm just going to get rid of it. It's going to be deleted. So we can do that by looking at our points and basically saying, let's get a list of all the primitives that this point is in. So we'll say point prims for this point. And then we'll say if the length of that array, so this array should be storing now all of the primitives that this point is a part of. If there are none there, that means this point is isolated. So if that length is less than 1, so if there's no primitives in there, we're just going to remove this point. So if we do that, sure enough, all those isolated points go away. We still have a few sort of loose little scraps here of bits that have just kind of come loose that have at least a couple of points in them. So, you know, this one has 3 points. It's a little triangle that's gotten loose. So we have a few of these things, but I think that that's okay. It's not nearly as sort of cluttering as those that swarm of individual points we had here. So all of those are gone. So that's a good first step. The next thing I might like to do actually, and you won't really see a major difference here, but for a final render and when you have sort of high resolution, it's nice to give it a quick smooth. This will curve out and sort of round some of these edges a little bit. It'll just make it a little bit smoother looking, a little bit more organic looking. As I say, with this current setup, you're not going to see that much difference here. It's just going to round things out ever so slightly. When you do have a full setup, I recommend leaving this off until you're ready to render, because this is an expensive step. Once you have sort of hundreds of thousands or millions of points, this starts to become pretty expensive. It's going to sort of slow things down a little bit. On the scale of rendering time, it's not really a big deal, but if you're just visualizing and testing things, this is something you're probably going to want to leave off. Now, the last thing we want to do is put in our coloring down here. So I'm going to replace this down here, and we'll see in a minute when I add some extra little tweaks why we might want to keep this down here, but in general, doing your visualization at the very end of the sim is usually a better way of going about things. So we're just going to drop basically that same color information we had up here down at the bottom. And so we'll just throw that in there. And in fact, I'll even go so far as to delete it from up here. So now this is sort of wrangled again, but if we run it through, we have that same coloring because we're doing it at the end there. Now, the last thing I want to do is just add a couple of maybe little tweaks to help this sort of be a little bit nicer to visualize and to give you a bit more flexibility in how you want to see it. And so in particular, the two things I might want to do, and you won't see this in the viewport, but once you render you will, I kind of like the idea that as these things start to shrink, so as they start to get sort of smaller than their original length, they should also get thinner. So when you render this as strands, you're going to be able to set up the individual sort of thickness of each of these strands. I like the idea of being able to manipulate that, to make that thickness vary depending on how sort of strained these individual strands are, or you could even make it vary based on depth. So basically just having some way to sort of control the thickness of these strands to give the appearance even more of this sense of contraction. So one of the easiest ways to do that is just to store the original length of these values. So I'm just going to do that right in here when we set up our constraint properties. I'm going to go ahead and say original length is our rest length at the beginning. So now, if we propagate through, I'll just get a little ways till we get some tearing. There we go. If we make sure to bring this value through, or rig len, I think is what I call that. Now if we look at this information, we have an original length and a rest length. And what we can do here is use those things in a primitive wrangle and basically say, well, what's our proportionate length? So we can say prop len is our current rest length divided by our original length. And this is going to be a value in 0 to 1. And so actually we could even visualize this. So let's just set up a primitive color here, because this is a primitive value, and we'll do a ramp, and we know it's actually from 0 to 1. And I guess we need to set this as an attribute here. So set that. Prop len is prop len. So if we take that attribute and scale that, and if we visualize this instead, you can see as they start to shrink, we start to get that color coming through. And you could use this as a color to visualize, so this is kind of an interesting visualization as well. The smaller they get, sort of the darker they get, or whatever ramp you put on here. But what I want to do is actually use this to drive the thickness of these lines when we render it. So to do that, what I'm actually going to do is say our p-scale, because that's what the renderer is going to use, that's what Mantra is going to use, that's what basically anything is going to use to sort of render the thickness of these lines. That p-scale, I'm going to use a ramp actually, and I'm going to call this thickness ramp, and I'm going to pass it this value, proplen. And the nice thing about this proportionate length is it's going to be in the range 0 to 1. Rest lengths are only shrinking, and original length was the original rest length. So this is going to start at 1 and it's going to go down to 0. So it'll always be in the range of 0 to 1, and that's what the ramp wants. So if we make this little ramp here, you can see we get sort of our nice control here. And we can basically say, okay, if it's near at 1, we'll keep it sort of at maximum p-scale. Down here, we'll come to our minimum p-scale. So maybe we want our minimum to be sort of even 0 potentially, but maybe we want some very small value. And this is going to be a multiplier on whatever we tell it up there. So some very small value, and maybe we have it sort of like a bit of an exponential curve. Maybe we give it this kind of a slope here. So it really gets thin very quickly, and then it only stays thick when it's really near its original length. So if we take this value, what we might actually do is just sort of multiply by this ramp. It doesn't like that when I define it that way. If I take our existing p-scale and multiply it, then we'll get sort of that value. Oh, now I've done something sort of foolish here. P-scale doesn't go on the primitives, it goes on the points. So we actually want this as a point wrangle, and that means we're going to have to sort of promote this prop length. So let me just move this down here as a point wrangle. We're going to assume that this is an attribute, it doesn't exist yet. So we'll set up this attribute here on our primitives. We can go ahead and delete this because we don't use it anymore. Delete spare parameter, that's fine. So we're just going to set up our proportionate length attribute here, and then we're going to promote it to the point level. So we'll do an attribute promote. So it's originally a primitive, we're going to promote it to a point. We're going to take our prop length. We can take the average, that's fine, because there'll be multiple different points, so that's all good. And then we feed that in here, and then we'll do that at the point level. So now our points are going to have these different proportionate lengths, and they're going to have a p-scale. And because we deleted their p-scale, we should probably bring it back. There we go. So now we have a p-scale here, that's the original p-scale. And as we come down here, you'll see this proportional length, so as it's sort of the same length as it started, this is 1, that'll stay at that p-scale. If we scroll forward until some of them shrink, you can see now they're getting smaller and smaller. So as these values are changing, the p-scale that it's using to render is going to also get smaller. And so this is just going to give that sort of tearing, nice finer look. So it's going to give it sort of a lot more of sort of refined and tight look as it starts to tear on these edges. We'll just pipe that back through. Ooh, yeah. And the last thing I might want to do as a tweak is give the option to actually put some kind of a texture on here. So instead of just coloring by layer, what if we want to put some UVs on here? What if we want to sort of take this from an original geometry and transfer over those UVs? And this is also really simple to set up. We just do it right at the beginning before we pass this through. So I'm going to take my original grid here, and I'm going to put some UVs on it. I'll just do a UV project, simplest thing in the world. So if we do a quick shade, just to take a look at that, you can see that's just going to set up our basic UVs just projected straight onto that grid, and that's just fine. So now what we want to do is basically just copy those UVs onto our points. So we'll do a point wrangle, and we'll grab this UV geometry and pipe it through, and we're going to use a combination of XYZ dist and prim UV to basically copy over to interpolate the primitives from that geometry based on the point distance. So to do that, we're going to need some variables to store some information. In particular, we want the primitive, and we want a vector UVW. I know we're talking about UVs, so this is going to be a little bit confusing. This UVW we're about to use is not this UV that we're seeing here. This is going to be basically a way to establish coordinates within a primitive. And we're going to use those coordinates inside of the primitive to read off the UV that we should put on this point. So to do that, we're just going to say xyz dist from geometry 1 relative to this point, and we're going to pass it these. So what we're actually doing is we're passing addresses. So we've basically created these two variables here, and what we're going to do is pass addresses to these variables so that this function can write onto these variables. So now that this function finishes, when it finishes, these two variables we've defined will carry the values that this function put onto them. So generally a function can only really give you one return value. This is a way around that. You basically pass it addresses to other variables and it copies values onto those addresses. This is also why we don't even really care about the return value here, which would be distance. We actually don't care about that distance. All we really care about are these two pieces of information. Now, using those two pieces of information, we're actually going to read back from this same geometry the value of UV at that closest point. So what we're really doing is storing information about the closest point on this reference geometry here, and then we're going to read back, using those coordinates, an attribute, in particular UV. And so UV will be interpolated based on where we are inside this primitive. So if I just do that really quickly, we're going to say UV on the point is going to be prim UV from geometry 1. We want to read the value UV. It will intelligently figure out that that's a vertex value, not a point value. We don't have to worry about any of that. And it's primitive, PRM, and at the coordinates determined by UVW. So once we've done this, now our points have UVs here. So if we scroll over, you can see we have UVs. And these are sort of what look like sensible UVs. They range from 1 to basically 0, and from 1 to essentially 0. Some of the interpolation isn't perfect, but essentially that's working. And if we drop a quick shade on here, I actually don't know if this works on points. It doesn't like it very much on points. What we can do instead, and we're going to move this to the end, but I'll just show it here for now. You can set CD using a function called color map. And color map will take a file. So this is going to be a channel string. We'll call that file name. And it's going to take a UV value, and this is UV. So this is basically just reading a texture onto the point based on some UV values. So if we set this up, we can toggle this to create this parameter. Now you could type this in, but actually what you can do is go into your parameter interface, now that we've created it, and you can change the type here. And you can actually go down and say, actually I want this to be an image browser, which is perfect. So we'll apply that, and now we get our nice toggles to be able to select images. So if we just go here and, for instance, go to some of Houdini's basic sort of built-in stuff, we can grab bricks, for example. And if we do that, now you can see that we've basically copied over UVs, and we can get this information coming in. This is obviously very low resolution. We only have 5,000 points scattered on each layer, so it's not going to look particularly good. But if you were to ramp up these point values and get a whole lot more points on here, you could actually get a pretty faithful reconstruction. So I don't actually want that up here, because if I want to change it after the sim, well, it doesn't make any sense to have it ahead. So we'll just pipe the UVs through into the sim. Then when we come up, we'll make sure to propagate those. So we're going to keep UV. And that means at the very end here, we can put that texture onto our values at the end. Now, this hasn't cached through, so let's just reset that. So there we get our bricks. And sure enough, as it goes through, we keep that UV, but it tears and keeps where those individual points were to begin with. And you can do a few interesting things with this. You can even merge these two values. So we can use, I don't know why that's there, scale that back down. We could take this color ramp, and instead of setting CD here, we can just multiply it. So we can multiply these two values together. And so now, as we go down through layers, they get darker and darker. They get towards 0. So there's a lot of different things you can do here with sort of shading and texturing and rendering and setting this up. But really, these are all just tweaks to give you a different look. So this is the basic setup, and using this you can pretty much tweak and adjust and make all sorts of different changes. You're going to want to sort of adjust these values to be a lot higher if you want a really nice looking sim, but for the sake of being able to actually run this during the tutorial, I set these values nice and low. The last thing I want to do is show you a little bit about how you can generalize this to other shapes, because right now it's just flat and we have it sort of wrapped into this scaffold here. You might want to do a lot more sort of interesting things with this. So I'm not going to build these from scratch because they use almost all the same parts, but I will show you a few other setups here, and I'm going to make this HIP file available. So in here we've got that setup we just did, so it's all sort of annotated and explained. In these two, I've got two alternate versions. So one of them is just doing this on a sphere. And so this is kind of fun, and what it gives you is you don't have edges anymore, so you don't have to lock the edges. What you can do is just sort of tear it on a surface. And if I sort of run through here, you'll start to see at the top there, we're starting to sort of tear away in this, in this region up here. And maybe I'll switch this to just a nice color node. Great. So you can see that this is now tearing on a sphere. And so there's a few differences to make this setup work, but it's roughly the same thing. And you'll be able to sort of walk through this file here on your own, so I'll just gloss over the most important parts. So we set up and we do our layers more or less the same way. We scatter on each layer, we make our constraints between the layers. The main things that change, we're going to copy over our UVs again, is inside, that's right, it's not even inside any particular node. When I scale my layers, in this case, instead of doing it in the copy transform, so here I just copied and I did no transform, so they're all layered on top of each other. For each layer, I basically just took the positions and pushed them outwards, and that's this function here. So I basically just took the position on the original geometry and pushed it outwards. And then I stored how far away from the middle. So because this globe is kind of centered at the origin, I basically just stored how far away from the center is this layer. This position here, when we go ahead and scatter, is on points, and so that means it gets carried through to each individual point. So all of these scattered points have this center distance function, and that ends up being critical, because basically everything else is identical, except in the POPnet, we've got this one extra node here. And all we do here is we basically make sure that this point is put back at the distance from the center it originally was. So if you think about what's happening while it's stretching, when it starts to tear and pull apart, some of these points are going to move inside the sphere or pull outside the sphere. All that this little step is doing is saying, okay, once you've done the solving for the pop grains, just make sure this point goes back to the distance from the center it originally was at. And so that effectively constrains these points to being on the same layer at the same distance from the middle that they started. And that's really the only difference in this setup from the plane. And you can see that that works pretty well. So all of these points are staying on their respective layers. We're not collapsing. We're getting this nice sort of tearing effect. Now the downside here is it's really relying on a single parameter, just how far from the center is it. So this only works for a sphere, which is sort of radially symmetric, sitting at the origin. And so it's not super generalizable. So the last one I've got here is this any shape setup. And this lets you use sort of arbitrary shapes, like you can see here. So I basically just took a bunch of metaballs and added a box to it. So there's nothing particularly special about this shape. I just wanted to show a very general shape. And in this case, you can sort of get, let me copy over that color node again. Let's put that in here. So here you can get sort of the same kind of tearing going on a much more complicated shape. So you can see them in some initial jostling as it tries to sort of figure itself out, but then we have our collision geometry is going to start coming through up here. There you go. And as we continue to sort of simulate here, you can see it spreads over this much more complicated surface. Now there are some problems with this. You'll start to see some of them, especially in here. You're starting to see that really early tearing. But in general, you're getting this tearing that's nicely following this fairly complex shape here. So this solution will allow you to generalize to more complicated shapes. The biggest issue you're going to see here, and I've got that, if you notice that big long note at the sort of object level, that note is addressing this. Where you have high curvature, you're going to get sort of strong breaking. And the reason is this reprojection, because if we think about sort of a nice flat surface with no curvature, if we have two constrained points, and one of them moves and pulls the other point along, once you reproject onto this surface, they're basically the same distance apart. If you're across something like a right angle, if a point here and a point here are attached, so imagine like this line here, if this point moves up, it's going to pull this point up in roughly this sort of vertical direction. When it reprojects, it's going to reproject back down here. So it's basically moved not nearly as much as it needs to satisfy the constraint. So as points move around these high curvature regions, their rest lengths, or their sort of actual lengths of the constraints, are going to change much more quickly than points moving along a flat surface. And that means because of this sort of reprojection step, they're going to stretch a lot more, they're going to snap a lot earlier. So in general, I put in this box here to illustrate that. I wouldn't use shapes with really high curvature unless you're prepared to do some extra work to sort of combat this effect. But if you have nice smooth shapes, like you can see up here, it doesn't have to be a sphere and it doesn't have to be at the middle. You can still sort of make this work. So if you have nice sort of smooth shapes, this will still give you a good effect. But if you have these sharp shapes, you're going to start to get really early tearing there. So how does this setup work? It's very similar to the sphere, but instead of using center distance, what we do is we basically displace using that same prim UV and XY distance trick. And what we effectively do is at the outset, when we're expanding these points, we basically find out relative to the original geometry, which is here, so relative to that geometry, what's the nearest point? And we find that position and the normal interpolated at that point, and then we sort of redefine where our position of this point should be based on those two values. So we do that at the outset, and we also do it in here in the solver. So at this step where we were adjusting to center point, we just do exactly that same code. We basically say what's the nearest point currently, so even as the points drift around, they find their new nearest point on the original geometry, they find the sort of normal associated with that point, and then they adjust their position to match that sort of distance based on their layer. And so by doing that, we get it sort of following this contour. So it's a very similar setup to the sphere, but a little bit more generalizable. So I hope this has been helpful, or at the very least interesting to some of you. I know a lot of people have been very sort of interested in this pop tearing stuff. I've posted a few of these types of videos, and people have always been kind of really interested, and a lot of people have asked me about sort of getting access to the hips. So I'll make this hip available. You can kind of browse through it, see all the differences, take a look at all the notes and the things that you'll need to sort of set up to make this all work. And otherwise, thank you very much for listening, and as always, if you have any requests or any sort of things that you'd like me to try to explain, I am more than happy to entertain those. Thank you very much, and goodbye.